Okay, so hi everyone. So we have to do to prove these curvature formulas. So our task today is curvature formulas. So let me recall what we did. We defined the curvature for a curve in space. So for a space curve, say R equal to R of t. The curvature of this we defined like this. So K at t we defined to be norm of dt ds. Okay. So this was our basically our curvature formula. So I just put it inside a fish like that. So this is a nice formula. It's an amazing formula, right? Because it's extremely extremely useful. I mean, and important. It's not obvious, to come up with such a definition, but it's a definition that turned out to be good and useful for conceptual understanding of things. But as I said, the definition is not useful for calculation. That's the drawback of the definition. So what is this? So the inside is, of course, the rate of change. I mean the inside, not the magnitude. Just the inside is rate of change of a unit tangent vector. So this is rate of change of the unit tangent vector with respect to arc length, right? With respect to arc length. And then we put this norm or magnitude sign, so this measures the magnitude. As I said, conceptually is very good, but computationally is almost useless. So we have to derive alternative formulas. So the first formula that I said is the following. You can just show that kappa of t, or k of t, is equal to, we can take rate of change of t with respect to the parameter t, which is the original parameter. In other words, I can just take dt, and then I have to divide this quantity by rate of change of r with respect to time, by norm of r prime of t. So divided by and this is the first formula. That's kind of better than this one. You will see why. So let's prove this. Okay, so what is dt with respect to t? I mean, well, let's start with what we're going to prove and then derive the formulas and so on. What is k of t according to the fish definition? K of t is equal to a norm of dt ds, right? But this dt ds I can write as dt d little t times dt little t with ds, right? Just using chain rule, not change rule, chain rule, right? Okay, now this we can just, because this is a vector and this is a scalar, so it just comes out of the vector sign. So this is equal to, I mean, magnitude sign. This is equal to an absolute value of dt ds times norm of dt dt. Right? So that's that. But then again, we can use this formula for the inverse function derivative, which is dt ds is equal to 1 over ds dt. This is also calculus. Right? So this is equal to, I just put here 1 over absolute value of dt ds. Also, I mean ds dt, sorry. Times norm of dt dt. Now the only question is, what is rate of change of arc length with respect to time? Can you tell me what this magnitude is? Yes.
The norm of R prime.
It's norm of r prime of t, right? It's exactly norm of r prime of t. So this is equal to 1 over norm of r prime of t. I derived this formula already twice, 3 times maybe. And times norm of, I mean, it's norm, not, yes, norm, and then times dt. Okay. So we started from the definition, the original definition, which was this definition, and we derived this new formula, which is the content of proposition, I mean, the first part of this theorem. Okay, so we can also write it as norm of t prime of t, the same thing, divided by norm of r prime of t. We can write it in different forms. So we can just write it out. So this is better because we don't have to use arc length parameterization for this. That's why this is more useful computationally. We don't have to use arc length parameterization. We can just use parameterization with respect to the original parameter t. But the drawback of this formula still is that this we have to compute a unit tangent vector. So you have to take derivative of this r prime of t divided by its norm, which is going to be some square root sign in the denominator, and then you have to work with that. So that's kind of awkward. So that's why the best formula for computing curvature is this formula that I'm going to prove next. Any question about this? Can you see over there? Maybe not. So I'm a bit off limit here. It seems, yes, that's better. Okay. Yes.
Why did you pull dt over d little t over ds outside of the magnitude? You said it was a constant.
Which one is it? This one? This?
Yeah, you pulled that out of the.
Yes.
Yeah.
That's not a constant. No.
Yeah.
That's not a constant, but it's a function, but it's a scalar.
Scalar.
So for each t, you can bring it out, and then that works. Because the whole thing is a function of t. The whole thing evolves in time. But at each point, you use rules of vector algebra at that point, and then you're okay. And because we are not differentiating this anymore, we are just using the result. So this is important. But here I have to be careful. You didn't tell me, you are not paying attention. This is not correct. There is one bar here and a double bar here. This is a very strange quantity. What would that be? We haven't introduced this concept yet. I don't think we will ever do that. So you didn't say anything, you didn't complain. You should have complained. Okay, that's better. It's just absolute value because it's a quantity. So there is a comment, I guess. Yes. Okay. There was a thanks. I don't know. Good. Thank you. Right. Now, so now the thing that we want to prove is this next result. Part 2 is the following formula: K of t is equal to norm of r prime t plus r double prime t, right, divided by norm of, I believe, r prime of t power 3. So that's the formula. And this formula, it's you can see computationally is a very good formula, because all you have to do, you are given this function, equation for the curve in 3D space, and you just take derivative, you just take second derivative and cross. You know how to do cross. And there is no need to go to find capital T. There's no need to do that. And so as a result, this formula is the best formula that we can have computationally. Of course, again, I emphasize, you notice that conceptually this formula is there's no meaning. I mean, what is this combinations of terms? If someone tells me this, it would be awful as a mathematical concept for me to take or to accept. But because we know it's a result of something more conceptual, we can accept it after we prove. So let us compute, because you see the formula is here. So let us compute T of t. What is T of t? The unit tangent vector. What is that? That's equal to, we know that it's r prime of t, right? Divided by norm of r prime of t. Right? But that's just a definition. Okay, let's cross multiply. We get r prime of t equal to norm of r prime of t times t of t, right? That's it. Now, this formula, formula 1, alternative formula 1 that we derive, suggests that we have to take derivative of t with respect to time, right? And I have everything here ready, so what I will do, I'll just take derivative of this on both sides. So here, I get r prime prime t equal to norm of r prime of t, right, times t of t. Maybe I'll just write it like this so that you know what is happening a little more clearly. This r prime of t, and then, so what we have done here, just take derivatives on both sides of this equation, right? That's what we do. Okay, so on the left-hand side, I get r double prime of t. Now, on the right-hand side, we use product rule for product of, this is a scalar function, this is a vector function, and we want to take its derivative. So product rule we know applies. So this is equal to norm of r prime of t prime, I just write it like that, times t of t plus, then I have norm of r prime of t times t prime of t. So that's this one. Okay, now what can you say about t prime of t? What can we say about t prime of t? Last lecture, and in fact, even a lecture before, so already I did this twice. You remember this experiment we had with unit tangent vectors or unit vectors? I said if a vector has constant length and moves in space, then its velocity is what? It is?
Orthogonal.
Exactly. Is orthogonal to the vector itself. Yeah. That's what. So in other words, t prime of t, which is velocity of t of t. T of t is a unit length vector, right? Is orthogonal to t of t. And now t of t is parallel to what? R prime of t, right? Because R prime of t is just t of t is R prime of t divided by its length, right? So this is parallel to R prime of t. This is not a norm sign, right? This is now a parallel sign. Sorry, this is what we have to use. So this is parallel sign. So what we have is that t prime is orthogonal to t, and the unit tangent vector t is parallel to R prime of t. Okay. So what I can do now, I can cross multiply this line by vector R prime of t. So this is now star. So I'm going to cross star by R prime of t. Okay. So next, cross star with R prime of t. We get the following equation: R prime of t cross R double prime of t, right? R prime of t cross product R double prime of t now is equal to this whole thing has to be cross product with R prime of t. So this is R prime of t. Then I've got the cross product, this vector, norm of R prime of t prime t of t plus norm of R prime of t times t prime of t. Right? Okay. So we know that t prime of t is orthogonal to t of t. So can you simplify these equations for me a bit now? For example, can you tell me what is the result of this? The first cross. So let me just write it. So let me not write it because, so can you tell me what is R prime of t cross the first term? It's 0, exactly. Why? Is parallel to tt, and tt is orthogonal to t prime of t, right? So we use both of these things. So this part is 0. So that's equal to 0 plus, then we have this term, norm of R prime of t, R prime of t cross t prime of t, right? So far we have reached this. Okay, so there was this difficult term that evaporated. That's good news. So we got rid of. Now we have this term. Now, can you tell me how can I replace this term? What is the value of this cross? Well, R prime and T prime are parallel, right? I mean, T of T is parallel to there is something here which I don't quite find. R prime and T prime of T. I say T of T is parallel to R prime of T, okay. Some mistake somewhere. Because I want to take a norm of this. No. Oh, that's great. Oh, we're in good shape. Let's take norm of this both sides. Get norm of r prime of t cross r double prime of t is equal to, well, this is 0, it's gone. So norm of this magnitude, well, the magnitude comes out. And then I have to take norm of r prime of t plus t prime of t. So what can I do with this, you think? Sorry? These two vectors are orthogonal to each other, so the cross product is going to be norm of this times norm of that times sine of 90 degree, which is 1. Okay? So this is equal to norm of r prime of t. Then norm of r prime of t. Norm of t prime of t, right? And the whole thing is equal to that side. Are you with me? Okay. So then I need this quantity. Because according to formula 1, I have to divide this by norm of r prime of t. So I just need this quantity.
Do you not need sine theta after?
What's that?
Sine theta afterwards?
Yeah, we need sine theta, but I said theta is 90 degree because these two vectors are orthogonal. Do you see why these two vectors are orthogonal to each other? Because r prime of t is along t prime of t, because, sorry, is along t of t. And I said that a unit tangent, a unit vector, its velocity is always orthogonal to itself. So if you, the only thing I'm using is this experimental fact that if you move this bar in space, while it's hinging on one point, the velocity of the tip of the vector is always orthogonal. So what does it really say? It says that if your particle is moving on a sphere, the velocity of the particle is tangent to the sphere, no matter how it moves. And that makes sense. Even experimentally, it makes sense. That's why, for example, by the way, yeah, I mean, this is a very good explanation. That's why when you're driving, on the surface of Earth, you don't get thrown out of Earth. Or, for example, when the ships, when they are like, sailing in sea, in oceans, no matter, you have a skido, for example, you're going really fast. Why you can go, you can do all kinds of maneuvers, but you never go up. Why?
You're not going fast enough.
No, you can go very fast, but you never get out of surface of the Earth by doing these sort of things, by moving on the Earth itself. The reason is this theorem I said, because your velocity is tangent to the surface of the Earth. So there is no component that pulls you out of surface of the Earth, no matter what.
You need to assume that the distance between you and the center of the Earth is always.
Is it well? Yeah, approximately is constant, right? Well, I mean, yeah, you're raising a good point. Surface of the Earth is, for practical purposes, I mean, in local areas, is a sphere. But you're raising a good point. The surface of the Earth, in reality, in large scale, is not a sphere. Yeah, it's kind of oblate, right? It's actually which one? What's the shape of the Earth? Do you know? Ellipsoid, but is it like elongated along the equator, or elongated more along the? How is it?
There's a question on this in the practice problems.
Oh, is that right?
Yeah.
Cool. So I better not answer it then. It helps me some thinking now. I was not sure about the answer. Okay, so anyhow, so let's not get carried away with that discussion. I really love this idea that if you move on the surface of Earth, no matter how fast you're moving, in what direction, in which way you move, you will never get thrown out of the Earth. That's this mathematical fact. That's all. Okay, very good. So now we are done almost. So here you get from here that, okay, so from here you get norm of t prime of t is equal to, you just divide left-hand side, which is norm of r prime t plus norm of r double prime t divided by norm of r prime t squared, right? So far so good, we derived this formula. And now I can use this formula and put it here. Put it in formula 1, sorry. Okay, so let me erase this part. Finally, using 1, we know that the curvature of t is equal to norm of t prime of t divided by norm of r prime of t. Not norm, sorry. Norm, of course. This is a vector, sorry. Okay, so this is, so I just use this information that I derived over there. I sub into this formula 1, and then I'm done. We are done. We did it together. Norm of t prime of norm of r prime of t plus r double prime of t over norm of, well, there is a factor of 2 and there is a factor of 1. They conspire and give us factor of 3. That's the source of this strange factor of 3 now. R prime of t to the power of 3. Okay? And that's it. And I can tell you, so far, perhaps this is the most difficult result I proved. I think this was most difficult, right? So far. We'll prove more difficult results later on, but this is, I think, I would say is one of the more difficult ones. Because it's not obvious, right? I mean, when you do the calculation in between, you sometimes say, oh, is it going to get me anywhere or not? So that's something. Any questions about this derivation? Okay, so there is a question, in fact. Oops, sorry. So yeah, Lindsay is asking, would it be perpendicular? So yeah, maybe I'm attending to the chat too late. Sorry. What would be perpendicular to what? Can you tell me? Yeah, maybe you are referring to something else. Yeah. You answered the question already. Okay, very good. All right, so this is the second part. But remember, the result I wanted to prove had another component. So that was the curvature for graphs, right? Let us prove that. So here, this is part 3, curvature of graphs in 2D. So in other words, you remember, we had this graph, and we wanted to compute the curvature at different points. So this graph was the graph of a function. So y equal to f of x. And the formula that I gave you last time, but I did not prove, of course, I'm going to prove it now, was that curvature at point x is equal to absolute value of f double prime of x over 1 plus f prime of x squared to the power 3 over 2. This is the formula. Okay, how can we prove this using 2? Well, a graph is also a kind of parametric curve, which is very simple. Right? That's the point. So proof using 2 and writing. The parametric equation of this curve. I have a graph which is y equal to f of x. It's in the plane. Can you give me its parametric equation? If I want to write it as in some parameter, how can you tell me the parametric equation of this curve? I have some answers. Do we need to know these proofs for the midterm or for the exam? No, you don't need to know the proof. I mean, it's good to know, but you don't have to it for the exam. I won't ask you the proof for the exam or for midterm, yeah. I will mention this in some clarification. Okay, so can you parameterize this? X, yes, exactly, f of x. 0, the third component is 0. Right, exactly. And you might complain that I'm using x here, I use t here, but who cares? I mean, this is just a variable. I mean, it doesn't matter at all. Just okay, so this is r of x. Okay, so then k of x is equal to norm of r prime of x plus r double prime of x over 1 plus prime of x. I mean not 1 plus, come on, this is nonsense. Norm of r prime of x to the power 3 over 2. This is equal to. So you can now calculate these things because r is given like that. Yeah.
Isn't it r to the power 3?
R to the power, oh, exactly, yeah. Thank you so much, yes. You're alert, that's good. Okay, so then we just have to compute that quantity then. That's very good. Of course, you know, sometimes I just put mistakes intentionally on the board just to see if my audience is alert or not. So you never know whether I made a mistake or not. Okay, so all right, so now what is r prime of x? Okay, that's equal to 1, f prime of x, 0, and r double prime of x is equal to 0, f double prime of x, and 0, and r prime cross r double prime is equal to ij k, 1, f prime, 0, and then 0, f double prime, and then 0, right? Okay, that's very good. Determinants that have a lot of 0 in them, they are very friendly because you can just easily compute. So what is that? That's equal to, well, the I component is 0. What is j component? That's also 0. Plus k component is just f double prime. Good. Okay, so k of x. So okay, so then so let me just calculate this. Okay. So what is norm of r prime plus r double prime? What is this norm now?
F double prime squared.
Is it?
Root, oh, it would just f double prime x.
It's just f double prime of x. Yes. But is it really f double prime? Absolute value, right? Absolute value. Not norm, absolute value f double prime. Why it should be absolute value? Why I don't write f double prime? I just write absolute value. Why should I take absolute value? Because norm is always positive. Or you can say it was really like this: f double prime of x squared, as you said first, but you notice it has to be under the square root sign. But the square root sign is never negative. It's, by definition, it's positive. So if you think a square root is plus minus this or that, that's not correct. The square root is always. But anyhow, but as you said, or you said, both are correct. So this should be absolute value. Right. Now, what about norm of the denominator? Norm of r prime of x squared, prime of x to the power 3. What is norm of r prime of x? Can you tell me? This is r prime of x. That's going to be equal to 1 plus f prime x squared. There is a square root, so 3. That's it. So you sub in, you get curvature at x equal to, indeed, absolute value of f double prime of x over 1 plus prime of x to the power 3 over 2. Oh, squared to the power 2. And that's the formula we wanted to derive. Any questions or comments? No. Good. So, okay, so we have these 3 different formulas, and the most useful is the second one, which is most general also, and the third one is for graphs, which is also useful, and the first one is conceptual, kind of, it's good for understanding to some extent. Now it's time to give some examples. So I'm going to erase this part. Any questions? Okay, so let's look at this example then. Y equal to, say, half of x squared. Compute. So example. So I'm going to say at what point, so x is between, say, 1 and 0, okay? So the question is at what point its curvature is maximum. So here is the curve. It's a parabola, of course. So we look at this parabola only in the interval 0, 1. Okay, that's good. And we want to know at which point the curvature of this curve is a maximum. What is your hunch? Your gut feeling about this? 0 is curvature maximum? Yeah? You guess 0? Okay. Calculate K of X and take FOC. What is FOC? Set the derivative to 0. Yes. Yeah, that would be the thing. Okay, so let us compute the curvature in general. Maybe we can avoid that calculation. Maybe we can be just a bit more alert and avoid that minimization problem by gazing at the equation itself. Okay, so then what is curvature of this guy? Curvature of X, so this is solution, is equal to absolute value of f double prime of X, or y double prime, divided by 1 plus y prime squared to the power 3 over 2, right? That's the, okay, so now this is equal to, what is y double prime? If you take derivative once, you get x, you take another derivative, you get 1. So that's good, that's 1 on the top. Good. So in the denominator, I've got 1 plus y prime squared. Now, y prime is, again, x, so this is x squared. And then we have got 3 over 2. So this is for x between 1 and 0. That's the curvature at any point. You see that? So now, can you tell me at what point the curvature is a maximum? Yes.
0.
Why?
Well, if you take the derivative of that, set it equal to 0, you get the derivative of that equals 0 at 0.
Oh, but then you have to, to be 100% kind of sure, you have to make sure that the second derivative is positive, negative, actually positive, for this to be a minimum. So you go on and on, right? So this is going to be a bit of a complicated equation you may get to solve. And then the second derivative even more complicated. So that's going to be kind of longish. It would work, for sure. It would work, but I'm saying you have to. Just putting derivative equal to 0 doesn't tell you it's a maximum or minimum, right? It's just a critical point. Any reason why? So any other guess where the curvature is minimum, where the curvature is maximum? Yes, exactly. Look at this. This is 1 divided by some quantity which is bigger than 1 if x is different from 0. So in other words, what I'm saying is that the maximum of this guy is obtained when the denominator is a minimum. That just makes perfect sense. Maximum is when the denominator is a minimum. And denominator is a minimum when x is equal to 0. You don't have to do any calculation. That's just plain high school or whatever, elementary school algebra, whatever. Okay, so this is, so I just say like this, K is minimum, it's maximum at x equal to 0. K is minimum at x equal to 1. Remember, we confined ourselves in the interval 0, 1. You see, we just said it. But now, if you allow yourself to go to infinity in the whole range, if you look at this function in the whole range, but x between infinity and bigger than or equal to 0, minimum is at you see, as x grows beyond limit, this function goes to 0. So there is no specific minimum. As you go further and further from the origin, the value of your curvature is going to decrease more. So there is no minimum for this. So the minimum is, and in fact, you may have a feeling that this is true because as you go up, this curve becomes more and more like flat, like a straight line, almost like a straight line. So that's what's happening. And the formula exactly reflects that fact. Infinity. So this was a good question, I believe. Okay, so, well, you can put derivative equal to 0, but not necessarily. This is this is a shortcut that helps us to solve the problem. You got it, Luis? Great, very good. Any other questions or comments? Now I have to introduce two more concepts. One is the normal vector, and the second one is binormal vector. So T of t, we did it, right? So this is equal to r prime of t divided by norm of r prime of t. This is called unit tangent vector. Now the second vector we are going to define is this normal vector n of t. This is equal to norm of, is equal to t prime of t divided by norm of t prime of t. This is called the normal vector to the curve. Normal vector to the curve. And finally, we define a third vector, which is b of t, which is t cross product with n. And this is called binormal. So if you look at these three vectors, something interesting is going on here, right? So the three vectors form a kind of orthonormal system that moves along the curve. So this is t of t, this is n of t, and this one is b of t. The right-hand rule said that if you put your hand here and move towards n of t from t of t, your thumb should direct along t of t. So, in other words, this is 90 degrees, this is 90 degrees, the other one is also 90 degrees. So this defines a orthonormal frame that changes from point to point. So this is called the Frenet frame. So at each point, there is this t of t, n of t, and then b of t. And here is t of t, n of t, b of t. So this moving frame along the curve is called a Frenet frame. This is the name of the French mathematician Frenet, was a great guy. Frenet frame. There's another guy whose name sounds similar to Frenet. You know, in optics, you have seen maybe it's called Fresnel, right? It's written Fresnel, it's French word, so Fresnel. That's not this guy. That guy was a great physicist, but he's a great man. He's a very good man. I wouldn't say great, but good man. Anyhow, so we have this moving frame. So this is a moving frame along the curve. It's just moving with the curve. The reason it's introduced is because you use these things in physics, in mathematics to study motion in space. Actually, we'll have some uses for that. Now, can you tell me why n is normal to t? I said it's normal. Again, this is for the fourth time, yes?
Because like you're using the p vector of the unit vector, which is orthogonal.
Exactly. So exactly. So this t is a unit is a unit vector, and we are taking its derivative. So this t is orthogonal to t prime. Right? But t prime is along n. It's parallel to n. You just normalize it by some norm, by some quantities. Same. So they really form an orthonormal system at this point. They really form orthonormal. And B is orthogonal to both of them. Well, I mean, this is the definition of cross product. When you have a cross product, the cross product vector is orthogonal to both vectors. So that's also taken care of. There will be some examples about these things, and we shall look at these questions later. Orthonormal basis, yes, that's called orthonormal basis. Exactly, yeah, that's exactly correct. Any questions or comments? Yes.
When you're getting the normal vector to the curve, you're
Yeah.
dividing the unitangent vector, or the derivative of the unitangent
The
vector
derivative, yeah.
by its magnitude.
Yes.
Why would you do that if the unitangent vector itself is made by getting rid of the magnitude?
Right, that's a great question. That's a great question, right? So the question is, we know that unit tangent vector is unit, so as magnitude 1, we designed it to be like that. Now I take its derivative, but the vector that's changing and has constant speed 1, if you take its derivative, it doesn't have magnitude 1.
Would it have greater than 1?
It could have anything. It just depends how the velocity at that point is changing. It could be huge. So you can see this in practice. You see, you can drive in a car very, very slowly, right? But your jolt could be huge. If you just change your speed quickly in that interval of time, but you could drive very fast, but your jolt will be very small because you're changing your speed slowly. For example, you step on the brakes smoothly, then you change your velocity in a controlled way. So you can practice all these things in real life, actually. All these statements we are making have real life implications, as you know, of course, because you're doing physics and all these things. So that was a great question. Yes. So the question was, we know that norm of t of t is equal to 1, but this does not imply that norm of t prime of t is equal to 1. And I want you to give an example of this for yourself. Just give some examples to convince yourself that that's also mathematically also. This does not imply. So that's why we had to divide by this guy. So I'm going to stop the video actually right now, and then we can just discuss. That's fine. Stop.